Hello, this is the second part and the final part of the moon rotation, moon phase rotation, and how it destroys the flat Earth. I will not keep you long. I will play the video, but I just want to stress on something, that when I say it destroys the flat Earth, because actually it annihilates any possibility for any model other than the heliocentric model. And I'm not saying the ball Earth, or only the spinning ball Earth, or the spinning ball Earth that goes around the sun. No, I'm also saying that the orbit is an ellipse and the moon goes around the Earth. So that's what I mean when I say the heliocentric model. I'm not just trying to prove that the Earth is a ball. So I'll go to the video and then explain how did I do it. Just a half-a-minute video. Yeah, before I start, you see this is the moon, and this is the terminator line, and this is my simulation for the terminator line, or in this case I'd like to call it my prediction of how the terminator line would look like on that specific date from that specific latitude. Then I'll start adding 1 hour in Stellarium and 1 hour in my spreadsheet. And before anyone says Stellarium is CGI, go use your camera, film 12 hours moon from rise to set, and tell me what's the date, and I'll do the prediction for you. So here we go. Notice 1 hour here and 1 hour here. How they're going, they're changing their weight like each other, and also the direction, which you're going to see now. Yes. And here's the flip, and they're still going hour by hour along with each other. Until the moon sets. So this also additional thing, I made a graph for azimuth and elevation. So how did I do this? I want to get back to the moon. Yeah, there it is. So first thing, I imagined two imaginary stars. One is slightly above the moon and one slightly below the moon. Two stars that are moving around the Earth with the same lunar rate. The moon is a little bit slower than the stars. And then as I track those two stars, they will be starting to switch or to spin around each other. Not the stars, in fact. It's because if you're looking this direction and then you're moving your camera and your azimuth to another direction watching the stars, then your field of view is going to change. So I don't, or I can't only use 1 point. I need 2 points, because as I see those 2 points, I don't know if you can see my hand or not, those 2 points, they are changing their elevation and azimuth as I'm watching them in the sky. So in the previous video I showed how, or just the basics of how can I deal with stars and know their location in the sky. So actually this application here, or this spreadsheet, this is what it does. It has low star and high star. And when I say low, it means less declination than the moon, and the high is high declination than the moon. The inputs for this application actually are 3. Now let's go here. I have the inputs, the usage for those inputs, and the heliocentric elements that I used to solve the problem. And you see here marked in yellow is the problems that I solved using the heliocentric model. So the first thing is the declination angle of the moon. I should know what's the height of the moon for height above the equator. Not height in distance. I mean, the declination is which latitude line the moon is perpendicular on. during Earth rotation. So I get the declination angle of the moon, and then I add to it half a degree and subtract from it half a degree. So those are my two imaginary stars. To track a pair of stars, and that we already covered, not completely because it's a long process, but I just explained how you can bring or calculate the azimuth of the star using your latitude and the star declination. So that leads me to the second thing here, latitude line. I need the latitude line to finalize the field rotation, and let me show you this. Yes, how the latitude affects our field of rotation when we're watching the moon. You see, this guy here is on the equator, and the moon, this is a side view. The moon is, this is not what he sees. Sorry, this is what he sees during moonrise or moonset. So the moonrise for him, the moon goes on top of him and then move to the other side. For that other guy on a higher latitude, the moon will be just going slightly up and then going slightly down. And if he's more higher than this and the moon is at higher declination, like here, then he's going to see the moon, like the 24-hour sun in the Arctic or North Pole or South Pole. So the latitude is a very important part of this solution. And as you see, latitude line means the angle from the equator on the surface of a ball. So this is the angle here. Take a line from the center of the ball with the declination, with the latitude angle, and then at the end there's your surface that you're standing on. So the surface should be curving. There's no other way to do it except this. Not concave, not you know, this one, convex or concave, I don't know what they call it. People say the sun is in the middle. Not flat, not anything, not cube. So this about the latitude. Now the next one. So the last one is the declination angle of the sun. And I think I didn't really stress on these points for the declination angle of the moon or the action of tracking a pair of stars. This was so clear from the previous video that we need the axial tilt, we need the Earth rotation, and of course because we're looking for the moon, then we need the Earth orbit. In the last video I showed a flat patch of land. That's why I say maybe the ancient civilization, they believe they live on a flat land, something like this, right? So but that flat land is tilted against a rotation axis for either the flat land itself or a sphere of stars spinning around this flat land. But if you move higher latitude, you must change all your calculation and base it on the sphere. The last thing is the declination angle of the sun. Why do I need the declination angle of the sun if I'm going to talk about the moon rotation? Well, actually, you can ignore it because the field rotation of the sky at night, you don't need the sun. But I wanted to simulate the terminator line, and the terminator line changes according to the declination angle of the sun. And let me show you this one here. So I hope you can see it well. This is the direction to the sun, and of course this is the terminator line of the Earth, and this is the terminator line of the Moon. The Moon is not sticking to the Earth. No, it's not kissing it. It's just the Moon, for the observer, that's us looking, is at the other side of the Earth, almost sitting. So for a person on the equator, he see the Moon terminator line tilted like this, or actually like this. But if we, that's during the summer, and during equinox, things change. If you are on the equator watching the moon set or the moon rise on the equinox, the terminator line should be horizontal, period, because of what you see now. And this is also one of the experiments or tests that I didn't add to my 11 tests. I can calculate the orientation of the moon phase based on the declination angle of the sun. Now, how to calculate the declination angle of the sun? Actually, it's one of the easiest things and most enjoyable things that I've done. You look here. Oh, I'm sorry. Well, this thing has been suffering a lot with me. The Earth, when the sun goes, when the Earth goes around the sun, what the sun sees is this: a rotation of the axis itself. So, if we presume that the sun is going around the Earth instead of the Earth going around the sun, for simplicity, and that's like the same other time when I said flat, stationary, a patch of land. If it moves from here in a certain period of time, let's say that's a quarter of a year or maybe half a quarter. We go to the next one. From here to here, now I can solve some triangles and finally use the 23.44 to get the declination of the Earth. But it's not that easy, because if the orbit was circular and here was the summer, then the equinox would be after a quarter of the period. But the orbit is not a circle, it's ellipse. So after a quarter of the period, it's here, not here. And this is like the actual Earth around the sun. Of course, it's exaggerated, but this is how it goes. The timing between the seasons are not the same. As you see here, we have from March to June, that's 93 days, from solstice to equinox to solstice, 93, 94, 90, and then down here is 89. The average is 91.25, around 25. So for this I have to use a bit of orbital mechanic or approximation for orbital mechanic, because it's so hard for me. I just make some clumsy math, but I still get a good results. So yeah, even though when I spoke about this tests, I said that it tests the 5 elements, but if you look here closely, you see that some elements are tested more than once within this only one test. So we prove the axial tilt 2 times, the sphere 3 times, the rotation 1 time, the moon orbit 1 time, and the orbit eccentricity 1 time. So I wouldn't have done that or any of that without Kepler. Now, flat Earth, I need some conscience, confirmed information, not hypothesis. You're just a walking zombie and you don't know it. Yeah, that's it. See you.